Hello everybody. Today's discussion will kind of accumulate all that we have learned. We have seen as a broad sense two different things. One is evolution of a system by looking at essentially variational integrals or variations of action. We learned Hamilton's principle here. The other thing we learned in last couple of lectures is transformations of the canonical variables. And these are not any transformation, these are transformation which keeps the canonical action or should I say canonical Lagrangian and or the equation of motion of same form. Today our aim will be to find out kind of relation between these two, and then we'll go to a new theory of generating dynamics of a system now by doing the canonical transformations. First, let us revise how we define the action. Defining the canonical action, say for example here. This actually goes for any action, but for the time being we are interested more in canonical action. For this I need a Lagrangian. I do it between two times. And we do it time integral of the Lagrangian. Where the system had some configurations. And this is also done along a path. I should not say trajectory, it's any path. So what is the case? So let me draw for you. Let me use blue for drawing here. So this is one point, this is the other point. I have a path. This point is at, say, t. Let me denote this as t1, and I have the position set as q1. Here it was t2, and say my position set q2. So that is the case, and I also, as I said, has to choose a path, and I have to choose a Lagrangian as well. Okay. So for the canonical action, we wrote down the Lagrangian earlier. It is S, which is given by, we wrote L this way, dt, between that initial point and the final point. Okay. Now we also looked at the Hamilton's principle, and that's what we used with the canonical Hamiltonian, canonical Lagrangian, to get the Hamilton's equations of motion. But let us do a different type of variation. What is this different type of variation? We say that the initial point is fixed. All right. So which means T1 and Q1 are fixed. Okay. Nextly, this is vastly different from what the variation that we are doing earlier. Here, remember in the previous case, we took many paths and calculated the action for all the paths. Here we don't do that. We say we choose the path only as the trajectory. Itself. So that itself is my path. Only the trajectory is the path. There is no other path. There is only one path. So, but then what do I change? I look at the action as it changes for different time when it will have different values of Q2. Okay. So what we are doing, we are saying that the initial point is fixed here. Then we are moving along this path only, and we are looking at the action at different time, where because it's in the trajectory, the Q's are all different, Q2s are all different. So in such case, it's obvious that the action, which is the value of this integral, will be a function of, what will it be a function of? Well, if I say that T1 is 0 and Q1 is, say, Q0, then these Q2 and T2, and hence the action will be a function of the coordinates and the time. Now, if I look at this equation, I can write down L as my ds dt, because that is apparent from this equation. Because, okay, So let us go step by step. So that equation now becomes S as a function of qi and t is just 0 to t, that's the integral I am doing, L dt. And you will agree that, so this I should write dt prime because that is a different time I am integrating over, but this is essentially as an indefinite integral L dt. So we'll agree that I can safely write ds dt equals my canonical integral L, which is nothing but, if you remember, pi qi dot minus the Hamiltonian, which is a function of qi, pi, and t. But S is also given by this, so I can write the total time derivative of S in terms of the time derivatives of its constituents. So del S del qi dot plus del S del t. That is just the chain rule of partial derivatives, and we can identify now two things. We identify that del S del qi is nothing but my pi just identifying the coefficients of qi dot from the two equations of del ds dt, and I also get del S del t plus h, which is a function of qi, pi, and t. This equals 0. And I can combine even these two and write del S del t plus h. Now h is a function of all qi's, which is alright, but it's also a function of pi, and the pi's are del S del qi, and function of t, and this is equal 0. And just to remind you, let me write this as S as S is a function of all qi's and t only. Now this is a partial differential equation, of S, which if you solve, we will get S. You get the action, which is all right at this stage. So I got a partial differential equation for the quantity we call action. And if you want to really solve it, we need how many initial conditions will we need? Well, S is a function of n qi's and one time. So we need n plus 1 constants. But if you look carefully, all the conditions that we have got, either this or this, there I always have partial derivative of S. So if I add a constant to S, then nothing changes. So this, because we have restrictions on some type of derivatives of S only, so we need only n constants. So I have the other constants, but that will always add up to s, and because everywhere I have derivatives of s, if I set that constant to 0, it really doesn't matter. Okay, so this is what I got from a little different action principle, where these are the conditions for the variation. So we vary only along the trajectory, and we vary the endpoint. We keep the initial point fixed and vary the endpoints. So doing that, I get these nice relations between the S and H. Well, that's all right. Let's see something interesting result from one of our canonical transformations. And the canonical transformations that we are going to look at is the one which is associated with the second type of generating function. So let me remind you of this canonical transform with the generating function I think we called it G2, which is the one where the capital Q was replaced by capital P. Okay. So this type of generating function, and if I have this, okay, so that is not all. I also today consider that it's a function of time. Okay. And what will I get then? So let us just work out what we did last time, but now with considering time also. So Pi Qi dot minus capital Pi capital Qi dot, and because it's a function of time, I will have to consider the difference in the Hamiltonians, and this will be equals dg2 dt, and then what you do is you choose g2, which is qi, pi and t, function of these, equals your old g, which is function of qi and capital Qi, and plus some alpha, and remember that I am replacing capital Q with capital P, so I should have summation of them, and I don't know what is alpha yet. And what I calculate dg d2 and keep it back here, so I get pi qi dot minus capital Pi capital Qi dot plus h prime minus h, and in the right hand side I get this minus that. The right hand side is not supposed to be this, so let me correct myself. This is supposed to be g0, so I replace this g0 there. So what I get is del g2 del qi dot plus del g2 del capital Pi dot, and then terms which comes with the from the terms with alpha, so alpha Pi capital Qi dot minus alpha Qi capital Pi dot, and because g2 is also an explicit function of time, So I will get another term which I may write here, del G2 del T. Right, this is all that I have got. So now, first thing we did last time is that we wanted to set these things added to 0. So for that we set alpha equals 1, and once alpha is 1, so this is 1. So that's basically, you can just not look at alpha in this term. So what do I get? I get my Pi equals del G2 del Qi, which is from this term and that term. And using these two terms, I get Qi as del G2 del Pi. But that's not all. I also have the time dependence now. So I get h prime minus h equals del G2 del T. Now here is the interesting thing. You see, in this box, I should also write del S del Qi as Pi. S here is action. If I take a partial derivative of that with respect to Qi, I get Pi, and then del S del T plus H is 0. Here I get similar thing, partial derivative of G2 now, which is the generating function of this transformation, with respect to Qi is Pi, and if I set h prime equals 0, actually if it is a constant then also it suffices, because in classical mechanics you can choose that you can add a constant to the Hamiltonian. Then when you take the derivative, partial derivative with respect to P and Q, that constant will not do anything. But let's say that I choose h prime equals 0, then I get this equation that del G2 del T plus H equals 0. And even I can go one step further. I can say that, well, del G2 del T plus H, which is the old Hamiltonian, it's a function of Qi, it's a function of Pi, but the Pi is given here. So this is del G2 del Qi and T. This is 0. This equation looks exactly the same if you replace G2 with S as this equation, right? So let's investigate what is happening. We see the following, that we start with a point which is t equals 0, where the initial values of q's were q0, and then we follow a trajectory. This is the trajectory of the particle. Okay. If I go at any point in the trajectory, the point in the trajectory, the value of time is t and the value of positions are q. So q, when I write, so it corresponds to all q's essentially. And corresponding to that, you have an action which is associated with this point now. As that point moves along the trajectory, the action changes. So the action has become a function of these quantities, which means essentially this action traces this trajectory. The action tells you what the trajectory is. And it turns out that if I consider the Hamiltonian in the final, so if I consider a canonical transformation of this particular kind, where the generating function is G2 type, and I consider the final Hamiltonian to be 0, then I get the generating function G2, which is a solution of the exact same equation that I got for the action. So this action is nothing but the generating function G2. The action is the generating function G2. When h prime is 0. Now what does h prime equals 0 means? So let's see what does h prime equals 0 means. H prime equals 0 will imply that del h del qi will be 0. So h prime is the new coordinates which I write with capital Q's, if you remember. This will be 0, which implies that qi's are constant. It will also imply that del h del pi's are 0. So these pi's are constant. Oh, that is interesting, because these are 2n constants that are required to solve 2n canonical equations. Right? Now, you realize the following thing. The canonical transformations are reversible. So if I have a Q and P, if I have a transformation which takes these two, capital Q and capital P, I should also have a reverse transformation which takes capital Q, capital P to small q, small p. Right? Now this is very big, because this, along with what we have discussed till now, will give us a very nice and interesting understanding. Let's see what we have got so far. We have realized that the action in this type of variations actually gives me the trajectory. Then we realized that if I would have chosen a canonical transformation with a generating function G2 such that in the transformed coordinate the Hamiltonian is 0, then that generating function is essentially the action. And then we realized that if the Hamiltonian is 0, the Q's and P's, capital Q and capital P's, are constants of motion with respect to that Hamiltonian. Well, let's reverse things a little bit. Let's say that I have this thing, and whenever we talk about evolution of the system, we always start with t equals to 0 or some known time, which you can call 0, and q and q's. And we ask the question, so q equals q0, and we ask the question at a later time and q, what is the state of the system, and that is now given by S, or if you wish G2. We realize that is a canon that's given by S, which is a canonical transformation from these variables to these variables, and these variables we are calling something, and these variables we are calling something. Now, because the canonical transformations are reversible, we can call these variables as capital Q and capital P, and these variables as small q and small p, without any loss of any generality. If it was not reversible, it could not say that. But if you do that, you see what happens. We had kept these fixed, which means that these are fixed numbers. Which is essentially what we said here, that the capital Q's and the capital P's as fixed numbers. And what the canonical transformation does, it essentially takes you from here to some other point in the trajectory. So the canonical transformation here, hence, so let me write the statement. Hence, if we choose Q's and P's as our initial condition, the small q's and the small p's gives rise to the trajectory. Okay. Now, obviously, it may not be so simple, because you remember that the Hamiltonian in terms of the small capital Q and capital P has to be 0. So sometimes you may need to do a canonical transformation from any initial system that you have to go to the capital Q capital P where H prime is 0, and then you proceed with this. Okay. So this, but interestingly, this is very interesting that this is now a single partial differential equation where you are solving for a single function as a function of qi's and time, and that time derivative is a single time derivative. It's not a double time derivative that you usually get in the other systems, in the usual Euler-Lagrange equation. And if I know that single function, I can now find out the trajectory. Okay, so this method is called Hamilton-Jacobi theory, and this equation, which I'll write down now more explicitly, is called the Hamilton-Jacobi equation. So let me write it in terms of S, because that is what people write usually. So having said that, let us see that given a problem, how do you approach to solve that problem? Because that is important once you have got this. Okay, so this has a lot of implications. One of the direct implication that I can tell you now, and you can read about it because I will not discuss it, I'll just give you the information, is this is a direct route to go from classical mechanics to the Schrodinger prescription, if you wish, or usually quantum mechanics. But let us not go there. Let's try to write down steps to solve for a trajectory using Hamilton-Jacobi equation. Okay, so what do I do first? First I write the Hg equation for the system. And what all I have to do here is that, first of all, I have made a mistake here. This is not S, this is H. What all I have to do is that I have to write my PIs in terms of del S del Qi. Okay, so that is what we do here and as well as here. So this is explicitly written here. So by writing PIs in terms of that's the first step. The second step is solve. This requires, as we discussed before, n constants let us call them alpha I. Okay, so I need n constants to solve these equations. So n is the number of coordinate, of course. I need those n constants to solve the equation. The third step, so once you have solved this Hamilton-Jacobi equation, the solution is in terms of these n constants. And we realize that these constants can be either these or combinations of them. So I can set what they are. So I set alpha i's as capital Pi's. Okay. So now what do I have? I have the generating function and all the constants are also set. Okay. So with this, now we'll do the following. Find the transformation equation. Using the generating function. This is what we have done before. You see, the problem of solving a dynamical system has become to first find the corresponding generating function and then find the transformation. So that's all the problem of solving a dynamical system has become. So what do I use here? So remember that del S del capital Pi is Qi and del S del small qi are Pi. Okay, so this, when you are doing this, also remember these are constants. So these are other constants. So let us set this to beta I constants again. And there will be n because I have n QIs. So let's see what will I have once I have done this. I will have Qi then I have Qi's as beta i's, and del S del Qi, what will that be function of? Del S del Qi will be function of some function of, this is coming from here, S is a function of Qi, and these alphas, because I have set capital P's to alpha, and this is this. Okay. So I can now invert whatever equation, whatever relation you have got in the form Qi equals something and Pi equals something. Okay. And that will be my solution, because this will have alpha i's and beta i's, which are the constants of the integration, which are the initial conditions, which will come in terms of the initial conditions that you need to specify the dynamic motion of the dynamical system, and you will have time and all, so that is the solution that you'll get. Okay. So this is the general prescription, and I will do the most simple case in the class, just because I can only solve simple problems, and you can work out the complicated ones, which will come as assignments. Example. What is the most simple example? Free particle. So what is the free particle Lagrangian? So if I write in terms of x and p, it is just half 1 by 2 m p square. Okay. So what is the Hamilton-Jacobi equation? Step 1, write down the Hamilton-Jacobi equations. So Hamilton-Jacobi equation is del S del T plus H, which is 1 by 2m. P square is del S del X whole square, 0. Now I have a time derivative here and x derivative here, and you see that h doesn't depend on time explicitly in this particular case, which means in the right hand side I cannot have any time dependence. The right hand side is h only, this is h only, which doesn't depend on time explicitly. This is not right hand side, but the right side of the positive sign. Okay, so keep that in mind. Keeping that in mind, I write, so now I am coming to this step 2, which is solve for the Hamilton-Jacobi. So the step 2, which is solve for the Hamilton-Jacobi, and I need I should be written this way, one constant. Let me call that alpha. I need one constant to solve this Hamilton-Jacobi. So S, I do a separation of variable, in this case in a linear way. Cannot call this S because that's already there. Let's call that A and B. These A and B. and you put that into your equation. So what you get is del S del T is nothing but del V del T. And let me write this in the right hand side. So I have 1 by 2m del S del x is del A del x whole square. Okay, now in the left hand side I have derivative of b with respect to time. So this doesn't depend on x. Similarly here I have a with respect to x. This doesn't depend on time. This is just coming because the Hamiltonian doesn't depend on time explicitly. So because of that, I can write the right hand side as the constant alpha, and I write it as minus alpha just because I don't want alpha to be imaginary. My mass is real, and this is a square quantity next to the mass 1 by 2m, which is real. So I write it with minus alpha such that alpha is a real quantity. Okay, so once I do this, I can solve separately for b. So b as a function of t is then minus alpha t plus some constant, let me call that c, and I also get that a as a function of x is, what is that? So that is 2 alpha m, and I have square of this, so I will get a square root of that, and then this is again just x plus some c1. So I get s as a function of x and t. This is the solution now. Which comes in terms of two constants. That is what was expected. So this is x minus alpha t plus I have c plus c1, but these are all complete constants, and as we said that the only partial derivative of s that does matter, so I even don't need to bother about this. So I can just set them to 0. So, and if I do that, I have got my solution for s. And it involves one constant. So I set that constant alpha to capital P, as we said before. If I do that, now I get s in terms of so because we will take derivatives with respect to capital P, this s depends what is the value of capital P, so I keep it there. The idea is to take the derivative first and then set it to a constant. Okay. Also remember, what was my Hamiltonian? Hamiltonian was p square by 2m. Okay, so let's come to the fourth step, where I use these relations, these two relations. So del S del capital P, let's calculate del S del capital P. So it will give me capital Q, which is del S del capital P, which is a little complicated, but still let me try to write down. The first term is, I write the second term for the first, and then I have root over of 2m I have p to the power half here, which is 1 by 2 root p times x, and that's it. That's the first thing that I get. What is the second one? The second one is del s del qi is pi. So let's do that. Del s del qi is pi. So what is del s del qi? Del s del qi. So let me write this down just in case. So it is del s del q, which is del s del x, that is equals p, and this is nothing but root 2 pm. So this implies, you see, that p is nothing but p square by 2m, which is the Hamiltonian. Nevertheless, I get this expression for q, which is root over of 2m 1 by 2 root p x minus t. And I have got the expression for p, which is now I invert this. When one inversion was already done, p is root over of 2 pm, and the other inversion q is we are calling it x, so let me just call it x again. What is x? X is okay, a little complicated, but let us do a little simplification of this, and then we'll write down what it is. So x is okay. First, let us write what is q, capital Q, in terms of small p. So I have root 2m here, I have half here, and root over of p, root over of capital P is nothing but p over root 2m. Times x minus t, which means capital Q is, so this gives me 2m in the numerator, 2 cancels out, so this is nothing but m by p x minus t, and that implies x is p by mq minus plus pt by m. Okay. Now let us try the inversion. Initial condition. Well, the inversion has actually already happened, but we have to set the initial condition first, and then that will give us values. So what is the initial condition? Well, t equals to 0, capital P was the p square by 2m, that is called p0 square by 2m because that is the initial value of p, it's equals to h. So q at t equals to 0 is nothing but m by p. T equals to 0, p is this, and we are calculating what is q. So at t equals to 0, we call p0 as p0 and x we called x0. So this is m by p x0 and t equals to 0. So minus t is minus 0. Now, as time progresses, q and p remains constant. Right? So what happens to x at a later time? X at a later time then is p by m times q, and q is now m by p x naught plus p, which is constant p naught, by m times t. Why did I say p naught is constant? P naught equals constant here in this particular problem, since p naught square by 2m is the Hamiltonian, and our Hamiltonian is a constant of motion. So hence, finally, we get the solution x equals x naught plus initial momentum by mass, which is initial velocity times t, p equals p naught. Well, that we know is the solution for a free particle which has a constant momentum and initial value of position as x naught. So this is the case of the free particle. Your homework, as you will see in the assignment, will be to solve for the Hamiltonian of a harmonic oscillator, which you know what it is. So this will come as your homework. You have to replace p by del s del x here also, but now your p, small p, will not remain a constant because you know that harmonic oscillator there is a force, so the momentum will change. Okay, so what we have learned today is that we started with the canonical action, and then we changed the action a little bit, the definition of the action a little bit, the variation of the action was the same, but the variation we changed a little bit, from where we got these equations. And then we realized that using the generating function g2, I can also get the exact same equation if I assume that the final Hamiltonian is 0. So it turned out that if the final Hamiltonian is considered to be 0, I can choose some capital Q and capital P as my final coordinates, which are always fixed at the origin or at the initial conditions, and then the generating function generates the trajectory. And this is what is used in Hamilton-Jacobi theory, which starts with this equation and follows these steps to calculate the trajectory. And finally, we looked at the most simple trajectory of all, that is the trajectory of the free particle. Turns out that it looks quite a complicated uh, set of things to get to even the free particle, but believe me that in many problems this becomes the only way of solving easily. Thank you.